vienu pēdējo tomēr inovāciju, ko es gribu jums arī parādīt, kas tika izstrādāta mūsu projekta ietvaros Itālijas Florences universitātē, kas arī pie mūsu projekta vērtēšanas tika no ekspertu viedokļa novērtēts kā pesimistisks un nesasniedzams rezultāts, bet kolēģi cīnījās, un vēl viens rīks, ar kuru viņi grib ievest emisiju monitoringu un arī kontrole, tas ir dronu izmantošana emisiju mērījumiem saimniecībās. Es varbūt atkal būs video, viens pēdējais video šodien, kas ir noslēgs mūsu semināru. Paldies par uzmanību. Mēs varbūt pēc tam vēlāk varam palikt, ja ir kādi jautājumi klātesošiem. Bet vēl par droniem, ka izaicinājums vislielākais bija sameklēt atbilstošus sensorus un izveidot iekārtu, kas būtu viegli paceļama dronam, lai nerādītu papildus izmaksas tieši ar drona izmēru un lidojumiem, un lai tie sensori būtu pietiekoši precīzi. Tāpēc arī pētījuma projekta laikā bija izstrādāta metodoloģija, kā sensorus pārbaudīt. Pirmajā gada pirmie izvēlēti sensori diezgan ātri tika atmesti un tika meklēti citi risinājumi. Un izstrādāta projekta laika validācijas sistēma, un šajā video būs arī parādīts, kā tie dronu sensori tika validēti un kādā veidā tas gala produkts tiek plānots rādīt un piedāvāt viņu tālāk tirgu, lai varētu precīzi katrai saimniecībai arī kolēģi iesaka šo ierīci izmantot kontrolējušam valsts iestādēm, lai noteiktu iespējamus karstuma punktus vai piesārņojuma punktus saimniecību līmenim. Es palūkšu palaist video, bet es no jums atvadīšos un vairāk neatgriezīšos. Paldies par uzmanību.
Climate change are growing problems, especially in food systems, which are considered one of the main sources of greenhouse gases emissions. Reducing emissions is one of the challenges to feed up to 10 billion people in 2050. To achieve these goals, it is necessary to develop efficient primary production systems with reduced impact on the environment, ensuring welfare and health of animals and operators. In addition, new systems for monitoring air pollutants are required to apply adaptive management strategies in farming systems. In this context, the University of Florence, in cooperation with experts in the field of electronic and informatics engineering, in the frame of the CCC Farming Era Net project, developed a decision support system that can be applied at various levels, from farm management to research, control and certification bodies and public managers. The main objective is to create an off-grid measurement system of air pollutants and greenhouse gases, for a real-time transmission to a server, its processing and subsequent consultation via web platform. The system is composed of a rotary wing drone equipped with a prototype control unit, specifically customized with suitable characteristics to host an optical and electrochemical sensor system. The sensors collect gas data in real time and provide georeference measurements that are transmitted to the cloud for further processing with proprietary algorithms and, finally, represented in a GIS environment for its correct visualization. During the meetings for the preparation and execution of the project, three major challenges emerged. The first was to develop a low-cost control unit equipped with high-accuracy sensors to collect and measure gases during flight. The second challenge was to create a small and lightweight control unit that could be used as payload on a drone and that would not considerably reduce the flight autonomy of the aircraft. And the third challenge, how to validate and test the developed system. For the realization of the first version of the control unit, the focus was on verifying the correct functioning of the entire system and, mainly, on the feasibility of the entire project. Basically, the system architecture is divided into 4 layers. Layer 1 is related to sensors for measuring gases. In Layer 2, the processing and transmission of the collected data towards the storage system is carried out. Layer 3 concerns data management and Layer 4 provides a tool for the correct presentation of the data. The functioning test and validation of the control unit and the sensors were carried out at the National Agency for New Technologies, Energy and Sustainable Economic Development, ENEA. ENIA is a public law body focused on research, technological innovation and the provision of advanced services to companies, public administration and citizens in the energy, environment and sustainable economy sectors. For testing and validation, the compartment with the central unit and the sensors were placed in a 15L electropolished chamber equipped with industrial sensors, at a temperature of 20 degrees Celsius and 50% of relative humidity. Gases were injected into the testing chamber following a gradient of concentration, which was simultaneously measured by the control unit and the chamber sensors. After the tests, measures were analyzed by means of statistical regressions that demonstrated the high performance of the unit to measure gases and particulate. In addition, calibration equations were created to reduce the reading errors of the system. Field tests were carried out on a livestock farm with approximately 450 dairy cows. 2 flights were performed on different days. The workflow included mission preparation, reconnaissance flight, mission planning and flight mission. The evaluated area encompassed all stages of production of the farm. Test results showed that the system clearly identifies the sources and levels of gas concentrations on the farm. It was possible to create maps of concentration and diffusion of gases in the total area of the farm. After carrying out successfully the field tests, the necessity to develop a common version of the control unit for ground and in-flight measurements emerged. The weight and size of the ground control unit were not ideal for attaching to the drone. Therefore, for the second version, we focused on reducing the dimensions of the control unit. Also, we plan to include an application inside Raspberry to remotely view the measurements and be able to download data. In order to carry out a correct redesign of the control unit and to improve the problems highlighted in the first version, a 3D modeling program was used to simulate the volumetric occupation of each component of the control unit. The new version of the control unit carries 9 sensors and a Raspberry board in a volume of 804 cc, with a total weight of 750 grams. A dashboard was implemented to remotely view the data. The dashboard can display information from several units at the same time. It is possible to observe real-time measurements from all sensors in the system in the same view, allowing a more dynamic analysis. In-flight measurements collected in the field need to be represented spatially. For this, the QGIS software was used to create a 3D map of the studied area and to perform an interpolation of the data, so that the spatial variability of the results can be investigated. In the tests carried out, the spatial distribution of particulate matter escape in a cattle farm was visually represented. Although the system has been calibrated in a specialized facility, a second laboratory test was planned under different environmental conditions. The second version of the unit will be placed into a climatic camera where field conditions will be simulated in a controlled environment, in order to evaluate the accuracy of the unit measurements compared to those from a commercial photoacoustic gas analyzer, in constant ventilation, but under different temperature and relative humidity regimes. Further improvements of the control unit will be implemented, to reduce its weight and improve its functionality. Field tests in livestock farms will be carried out, in order to optimize a measurement protocol for emissions assessment.